Hello, my name is Barry Mulvey, and I will be presenting on DeforMoBot, a bio-inspired deformable mobile robot for navigation among obstacles. This work was completed with Felina Lalitharatne and Thrishantha Nanayakkara at Imperial College, London. Navigation around movable or compliant obstacles results in a loss of efficiency and possible mission failure compared to progression through them. In this work, we propose the design of the deformable mobile robot DeforMoBot. The ability of animals, such as cats, to morph their shape to traverse spaces smaller than their natural body states is the bio-inspiration for the design of our robot. The specific contributions of this work are the design of DeforMoBot, the bio-inspired deformable mobile robot, the development of a shape adjustment algorithm in response to proprioceptive feedback, and the real-time estimation of the optimal robot body shape for traversing obstacles and fitting through narrow apertures. Our robot has a hexagonal shape, which is robust and strong under compression. A linear guide rail acts as its spine, and spring-loaded whiskers are attached to its front tip. The robot body, mimicking the transversal contraction of the cat, can change from a regular hexagonal shape to an elongated rhombus about 2/3 of its original width. We derive expressions for the robot's measurements given its angle of deformation, which is directly influenced by the servo angle. Applying geometric properties, we derive the robot's angle of deformation, which can be used to calculate its width. Our proposed robot control node takes feedback from the position measurement and shape controller and communicates with the motion controller and position to shape mapper, or PSM. A magnetic encoder at the tip of the whiskers communicates deformation measurements to an onboard Arduino Uno. Motor-driven rimless wheels at the front provide traction and grip, while passive omni wheels at the rear assist with the shape change, which is controlled with a digital servo. The wheels and servo are powered by LiPo batteries. The overlap of the comparison between kinematic analysis and experimental measurements demonstrates a good fit. The proposed PSM model compares the relationships between the different angles, which can be modeled as quadratic polynomials. We present an algorithm for obstacle traversal, which takes account of both the whisker angle and current body shape. The quadratic polynomial from the PSM uses hand-tuned coefficients to couple the whisker and desired body shape, which must be complementary to elicit meaningful behavior. We conducted experiments to observe how the robot interacts with different obstacles, namely boxes, cushions, clothes, and stone blocks, since these cover a range of different physical properties. The obstacles were placed apart closer than the narrowest possible width of the robot. We tested the robot across various approach angles, including 90, 60, and 30 degrees. Smaller angles are more challenging since the gap is tighter. The robot adjusts its body shape as much as it needs to traverse the obstacles. Where it can push away lighter or more compliant obstacles, it does not need to compress its shape as much. When it faces heavier or less movable objects, it compresses itself more until it has traversed the obstacles, at which time it can resume its normal shape. In all but one of the 12 cases, the robot achieved 100% success rate. In the single other case, stone blocks at 30 degrees, the robot achieved 60% success rate. The box plots show summary statistics of the distances recorded across the trials. The servo angle is reactive to the whisker in real time, apart from a rewidening delay so that the robot does not become stuck. Heavier obstacles result in steeper gradients. The quadratic relationship between the whisker and servo angle changes is shown in the lower plots. In future work, it will be interesting to explore the marginal gains of adding more degrees of freedom for deformation and more sensing modalities. In conclusion, this work presents DeforMoBot, a novel, bio-inspired, deformable mobile robot. Enabling the robot to adapt its body shape allows it to successfully traverse obstacles and fit through gaps smaller than its natural shape. Our results highlight the importance of co-development of environment perception and physical reaction capabilities. These capabilities will facilitate improved perception and proficiency of robots, resulting in their ability to navigate efficiently and effectively, particularly in unstructured environments. Thank you very much for your interest and attention.